Is that better? Okay, thank you very much. It's a great pleasure and honor to be invited here to speak at this conference honoring Abdus Salam. I first met Abdus when I was a young postdoc coming to visit ICTP in Trieste for the first time. And I wasn't quite sure what to expect. I knew that he was approaching 60 and I'd learned what to expect from some of my more senior colleagues in other places where perhaps they were less engaged in the subject than they had been in their heyday. But it was a great surprise and delight to find just how engaged Abdus was in all the latest developments, how full of questions and ideas he was, and what an inspiration he was. It was also very interesting to see how he managed to combine all the different facets of his life, his family life, his work at ICTP, and his scientific life. One problem which came up while I was there, I was giving a seminar at a time when he was also looking after his, at that time, very young daughter, who was perhaps age 2. And he had a particularly characteristic solution to how to deal with that problem. He brought his daughter along to the seminar. He sat right down in the middle of the front row, sat his daughter on his lap, and being Abdus Salam, everything went fine. As a speaker, I was full of trepidation as to what might happen and what interruptions might emerge, but with Abdus, everything everything went very smoothly. So I'm going to be talking about some aspects of string theory, in particular aspects of symmetry and geometry, and it involves. So I'll be talking about two ideas which played a central role in was of central interest to him. Of course, the idea of symmetry, and in his later years, he was very interested in the role of possibility of extra dimensions. And it's those two ideas I want to try and explain and discuss today. So string theory, or M theory, which is the theory which in some sense underpins string theory, the as yet mysterious non-perturbative theory which string theory emerges from. It's a rich theory with a number of novel features, in particular novel symmetries, which will play a role today, and exotic structures. But as yet, we're missing a fundamental formulation. We have a number of approaches, each of which tells us some very interesting things about it. A lot of work is done based on the supergravity limit, the low energy limit, which describes the light fields. But this misses many of the intrinsically stringy features of the theory. Another approach is to think of it as in terms of an infinite number of fields, so a finite set of massless fields and an infinite tower of fields of higher and higher masses coming from the higher harmonics of the string. But this picture misses some of the dualities and other symmetries which mix all these fields together and make them part of a single whole. A lot of work in string theory is developed from the point of view of the perturbative string, from a study of the world sheet theory, a study of the quantum mechanics of world sheets moving through space-time. But again, this is almost by definition makes some of the non-perturbative structure hard to reach. The success of field theory in particle physics was attempts were made to mimic that in string theory by developing what was known as a string field theory, a set of fields for representing strings. And this captures some of the interesting features which are perhaps not so evident in some of the other approaches, in particular some of the structure of the interactions and the algebraic structure underlying that. But all of these things are missing some of the features, and I want to talk about some work which is trying to understand some of the structures which one will want to understand from any more fundamental formulation. So a conventional picture is of strings moving in some geometric background, some smooth space-time equipped with a metric tensor and perhaps various other fields. And the fluctuations around this background are described by the modes of the string. So the perturbative graviton is described by one of the modes of fluctuation of the string. But this whole picture is very treats the background and the fluctuations in a very asymmetric way. In particular, for example, the fluctuations of the metric are treated very differently from the background metric. And one would want a more so our experience of general relativity would suggest a more democratic formulation would be much more would be very useful. One would want to understand in more detail what this would mean for the way that string theory modified the geometry. It might be useful, for example, in understanding this, how space-time singularities might be resolved. And one of the features of string theory, which I want to talk about today, is that there are various duality symmetries which mix geometric and stringy modes in an intrinsic way. And one of the features we want to talk about is that these kinds of ideas lead to a more general kind of understanding, a more general kind of background than the conventional space-time. In particular, the string theory has solutions which are not geometric in the conventional sense. And this richer set of backgrounds means that there's potentially a much richer landscape of stringy backgrounds. And some of these have features which are quite desirable in that, for example, some of the moduli or scalar fields one would want to try and stabilize become stabilized by developing scalar potentials in these backgrounds. So I mentioned duality symmetries. These started off from work in supergravity, pioneered in particular by Kremer and Julia, where it was found that certain supergravities had continuous classical symmetries. And typically, for the maximal supersymmetric theories, maximal supergravity theories in 11 minus d dimensions, these would be the exceptional groups ED. So in 4 dimensions, we'd get the exceptional group E7 arising. However, these are broken in the quantum theory, and also if one looks at deformations of the supergravities by gauging, then the gauge interactions explicitly break these symmetries. However, in string theory, remnants of these symmetries are found to be exact symmetries of the quantum theory. Typically, these are discrete quantum symmetries, and these seem, and in many cases, these are not things which can be understood in terms of classical field theory symmetries. So, perhaps one of the more familiar examples is one of T-duality, and I'll tell you, I'll explain more about this in the next few slides. This is one which is a perturbative symmetry of strings moving on the torus, and it has something which mixes conventional momentum modes or particles with solitonic states where the strings wind around compact dimensions. And then this extends to other kinds of dualities, for example, U-dualities, which are a non-perturbative extension of the T-duality, which involves mixing momentum modes with states involving branes wrapped around compact cycles. So these play a role in the geometry in a number of ways. So first of all, let's think about how one constructs a space-time. One thinks about space-time constructed from local patches, which, from the point of view of the physics point of view, these would be local inertial frames. From the mathematical point of view, these would be little patches of Rn. And then one would use the symmetries of the physics to patch together the local data to try and find a more global structure. So that patching with diffeomorphisms or reparameterizations would give rise to constructing a manifold. Patching using gauge symmetries would construct a gauge bundle or a Yang-Mills structure over the manifold. String theory has these new symmetries I've just mentioned, not present in the field theory, and these allow the possibility of constructing new non-geometric type backgrounds. so that patching with T-duality would lead to what's become known as T-folds, with U-duality to U-folds, and so on. And the other part of the story I want to discuss is that of extra dimensions. The story starts off with Kaluza-Klein theory, where adding extra dimensions to space-time provides some interesting structure, considering general relativity in a higher dimensional space-time, where some of the extra dimensions are compact, gives rise to a geometric origin for gauge interactions, and gives rise to a spectrum of massive states in addition to the familiar massless ones. String theory is something which incorporates this idea. Superstring theory necessarily lives in 10 dimensions, and its extension to M theory necessarily lives in 11 dimensions. The extra 11th dimension arises from non-perturbative effects in string theory, so that perturbative string theory only sees 10 dimensions, but at the non-perturbative level it sees an extra hidden dimension. One of the things I want to talk about today is that the duality symmetries suggest that the strings in fact see further dimensions. The strings on the torus see a doubled space-time, and so that one ends up with a picture where one has fields which become known as double fields, which depend on this higher dimension. But these are rather peculiar in that there's the full theory seems to be not a conventional local theory in this doubled dimension, in this doubled space, and I will say some more about that. And this leads to a bigger picture of a question about whether there could be an extended space-time as an arena for understanding M theory. So I'll say some things about that, and this will also be something which will be discussed further in Peter West's talk later this afternoon. So let me return to the question of strings on a circle and the duality symmetry which arise there, and then to strings on a torus. So if you have a particle on a torus, the momentum on a circle, its momentum will be quantized in units where h bar is 1. The momentum will be an integer divided by the radius. And if a string winds m times around the circle, it will have a winding energy which is the integer m times the radius times a dimensional variable which is proportional to the string tension. And the energy of the string is involves p squared plus w squared, the energy squared, that should say, and then there'll be some other terms. And T-duality is an exact symmetry of the perturbative string theory, which interchanges the momentum and the winding, the integers m and n, and the radius with 1 over the radius. And so states could be, so the theory could be labeled by the momentum and winding, or we could Fourier transform p to give the periodic variable x, which is the coordinate on the circle, and the discrete variable w could be Fourier transformed to give the coordinates on the dual circle, x tilde. And we could think of this as giving a space which is a doubled space consisting of a circle plus a dual circle, one with coordinate x with radius r, one with coordinate x tilde with radius 1 over r, and a symmetry, a T-duality, which relates these two different coordinates. So this gives a stringy symmetry which is not conventionally present in field theory, and this extends on a D torus, or a D-dimensional torus, to a T-duality group ODD Z, the discrete set of matrices in the ODD group. So integer-valued matrices in ODD, and this includes these transformations, a Z2 of this kind for each of the D circles. So if we think about strings moving on a torus, each coordinate is a function of could be thought of as a function of the worldsheet coordinates, a periodic coordinate sigma, spatial coordinate for the closed string, and a time-like coordinate on the worldsheet. And it's the solution of the free wave equations means you get a left-moving piece plus a right-moving piece. And it's useful to introduce an x tilde, which is the difference between these two. so x, the zero mode of x is conjugate to momentum, and the zero mode of x tilde is conjugate to the winding number. And this could be thought, so introducing the x and the x tilde could be thought of as an analog of introducing an electric and a magnetic potential. But the difference here is that from, say, introducing a magnetic potential in Maxwell theory, is that the interactions depend explicitly on this x tilde. This could be seen explicitly from the form of the vertex operators, which depend separately on xl and xr, or equivalently x and x tilde. And the strings, so the strings moving on a conventional torus will in fact see a doubled torus. They'd be described by both a function x of sigma and tau and a function x tilde of sigma and tau. And the T-duality group ODDZ then acts naturally on these doubled coordinates. So this structure has been known since the early days of string theory, but then this is very suggestive that this double torus is suggestive that there really is a double geometry underlying this structure. And this is something which has been investigated by many people over the years. And so this is a story which I want to develop a little today. So I mentioned that we could think about using the symmetries of the theory to construct, to patch things together to construct a solution. So if one uses T-duality, then this could be thought of, so here's a caricature of the kind of structure one can make in this way. One could have a space-time which had a sort of involved something which could be represented by a big cylinder with radius r and a small cylinder of radius 1 over r. And we could consider gluing these together. In general relativity, the metric would be discontinuous here, and this would not give rise to smooth fields, or such a discontinuity would be observable. But in string theory, one could glue momentum modes here to winding modes here in such a way that the physics was smooth over the join, even though it was not giving rise to a conventional smooth geometry. So this caricature picture gives an idea of how some of the new kinds of structures which might emerge in non-geometric backgrounds in string theory. So we could think of it more generally as a case where you had a patch of space, which might be represented in the previous slide by the length of the cylinder, and then a torus sitting over that, and then over another patch, another torus. And we could try and glue these together if we combine the metric and the B field together into a general D by D matrix on this torus. Then T-duality allows this kind of strange non-tensorial, non-linear kinds of gluing together, giving rise to something which will have which would not make sense in general relativity, but gives a more general kind of background which makes sense within string theory. And the key point is that the physics is smooth, as the T-duality is a symmetry of the physics. And here we're seeing that this T-fold transition, if we would think in terms of the doubled picture, it's necessarily mixing the x's with the x tildes. And this gives a key to how to understand this kind of structure. If we replace each of these tori with the corresponding double torus, where we include the x tildes as well as the x's, then these strange transitions turn out to be something which is a smooth geometric transition in this picture. And as a result, the space with the doubled tori becomes a smooth manifold with the T-duality acting geometrically on this doubled space. So this is the first clue that this double geometry might actually be meaningful, that whereas we get something where the undoubled geometry doesn't seem to make sense in conventional terms, the doubled torus seems to gives rise to a smooth geometric space in terms of which the field theory might look more familiar. So let me return now to the question of extra dimensions. So if we think about a theory, a supersymmetric theory, compactified on a torus, then it will give rise to a supersymmetric theory which has various charges arising in the supersymmetry algebra, which are carried by BPS states or supersymmetric states. So some of these states, some of the charges that are carried on the right-hand side of the algebra can be understood as momenta for the extra dimensions. And there are other ones which can be understood in terms, for example, of charges of wrapped branes or wound strings winding around some of these circular dimensions. But in the case where you have a symmetry relating these kinds, both these charges and these charges, there's a sense in which they're all on the same footing. It's like an extension of the Lorentz algebra, which is saying that all of these charges are on the same footing. And so this is suggestive that if these could be thought of as momenta in extra dimensions, maybe there's a sense in which these might also be thought of as momenta for further extra dimensions. And so this suggests that maybe we have a space where, as well as having coordinates conjugate to this momenta, PM, there are also further coordinates conjugate to these momenta. So leading to the question about whether it makes sense to try and think about this theory in this kind of extended space. So there's been a lot of recent work in taking conventional supergravity theories, typically ones in a space where the space-time factorizes into a d-dimensional piece plus another piece, so product spaces or warp product spaces. And in those contexts, it can be written in a way in which in terms of these kinds of extended spaces, in a way in which there's a manifest duality acting on, in which a duality symmetry of a certain kind is actually manifest. But the fields themselves just depend on a small subsector of the coordinates. They don't depend on the extra coordinates. So in this way, it's a rewriting of conventional supergravities, but in a suggestive form. So using this structure locally, allows us to give a picture where we can think about some of the kinds of non-geometric spaces I mentioned, for example, T-folds, by using these more general kind of transition functions. As I'm going to explain in a few slides' time, this structure is, in some cases, rather misleading because the actual stringy symmetry of the theory can be quite different from this supergravity duality. And so this raises a big question about the extent to which this kind of structure can be background independent. However, it turns out that in string theory, you can do rather better than in the supergravity theory, giving rise to a double field theory, of a way which I'll explain in a moment, with fields depending explicitly on the x's and the dual coordinates y, which are the things I was calling y tilde before. So let me say a little bit about this, and then I'll return to the more general story. So this is something which, this approach is something I've developed with Bartlett's feedback, and I'll make some comments about how this relates to earlier work in a moment. This arose from looking at a sector of string field theory which features some stringy physics, including T-duality, but in a much simpler setting. So it's one where one might hope to approach some of the stringy questions in a rather robust way. And the key feature is that the strings really do see a doubled space-time. And this structure is something which is a necessary consequence of string theory. It gives rise to the sort of geometric structure which is needed for non-geometric backgrounds. I mentioned earlier that one of the motivations which led to this program, which was trying to understand the geometry of non-geometric backgrounds and how the extended geometry gave rise to a smooth geometry there. And this leads to important questions about what is the geometry and physics of this doubled space. So if we think about strings on a torus, as I mentioned, each state is labeled by a momentum for each circle and a winding number for each circle. So I'm thinking of the space as being a product of a torus with, say, flat space, and I'm just going to focus on the torus dimensions for now. String theory in Minkowski space could be expanded to, in modes to give an infinite an infinite set of fields. In this doubled space, in this case, it gives rise to an infinite set of fields depending on both momentum and winding, or if we Fourier transform to a coordinate and its dual coordinates. And this double field theory comes from the closed string, necessarily has some non-locality in this doubled space. But it gives a structure in which T-duality is a manifest symmetry. And much of the work has been done on looking at for a subsector of a finite set of fields. And so we'd end up with, for example, a metric which was a D by D matrix depending on 2D coordinates. So the result is that the general solution of the string theory necessarily involves such doubled fields. And I want to stress that there's a real dependence on the full double geometry which arises in this way, where the dual dimensions are not an auxiliary or a gauge artifact, and so that the full double geometry is both physical and dynamical. Much of the work which has been done on double field theory is looking at a small subsector of this structure, which restricts to a subsector in which the extra coordinates do become essentially auxiliary, in which we recover conventional field theory locally. And in this case, one recovers a duality covariant formulation of the supergravity of a form first found by Warren Siegel. So we could ask about the extent to which this could be extended to M theory. As I mentioned, there's been a lot of work in which 11-dimensional supergravity could be written in an extended space in certain circumstances of product spaces, for example. And there's questions about the extension of this to the full M theory. And so one can ask whether something like the double field theory could be expected to work here. And the double field theory works in string theory partly because we have this picture in terms of string field theory, which gives rise then to the double field expanding out gives a double field story. So if M theory were a perturbative theory, say, of membranes, this would lead to a picture where one had extended fields depending on both XM and two brane coordinates YMN, say. But it doesn't seem to be such a theory, at least as far as we understand it at the moment. For example, we don't have a formulation in terms of an infinite number of fields. Nonetheless, the extended field theory does, however, give a duality symmetric reformulation of the supergravity, but the extension to M theory seems more problematic. So let me say a little bit about some of the structure here. Let me take a particular example of saying a particular supergravity in 10 dimensions compactified on a 4 torus. The duality symmetry here is one of the exceptional group series, which in this case is E5, which is just the group SO55, where the BPS charges are in a 16-dimensional representation. And there's been work by these people in rewriting the supergravity on a product of a 4 manifold with a 6 manifold as an extended field theory where you have an extra 16 coordinates representing these charges. And there's a similar, and this raising the question about whether this SO55 could be seen as a real symmetry in 10 dimensions. And there's a similar story for other product spaces. So I want to just, Peter West has been developing a different story where he's considering more general 11-dimensional spaces with an infinite set of coordinates and fields, but that's not what I'm talking about here. I'm just talking about, and we'll hear more about that later. I'm talking, in Peter's talk, I'm talking about these kinds of theories of these authors. And the problem comes if one tries to extend this to string theory. And for the string theory, we get a discrete subgroup of the SO55Z of the group. We get the U-duality symmetry group SO55Z, and this suggesting perhaps a realization of this in 6 + 16 dimensions. But for other backgrounds, the symmetry seems rather different. So for example, if we consider the theory on K3, The U-duality symmetry is SO420Z, which neither of these is a subgroup of the other. So, and it seems to be that these are disconnected branches, and there's this one, for example, is suggestive of 6 plus 24 dimensions, which is in fact what one gets from the double field theory of the heterotic dual of this. And there doesn't seem to be a smooth way of thinking about the geometry in a way which would apply to both this case and this case, at least in the context that I've been describing. So in this sense, the duality symmetry seems to be background dependent, and it makes a background independent formulation problematic. So time's running short, so perhaps I'll go to the, I was going to say a little bit more about the details, but let me go to the conclusions. The duality symmetries lead to an extension of geometry to allow non-geometric back solutions, and it's leading to a picture whereby this gives a simple and concrete understanding of a way in which we go beyond the conventional space-time of general relativity to allow a more general kind of structure. For string theory on a torus, we have the T-duality symmetry which I've been discussing, where one has winding modes and giving rise to a double geometry, and the understanding of string theory in terms of an infinite number of doubled fields. In the double field theory, if we look at the small subsector of the double field theory where we impose the strong constraint, it gives a way of writing conventional supergravity in a duality symmetric formulation of the form written of Siegel's duality symmetric formulation. But more generally, this applies locally in patches, and by taking into account the transition functions and so on, it gets a more general structure allowing these non-geometric backgrounds. The full theory with the weak constraint is non-local and it's essentially stringy and rather novel. In the work with Sviebak, we constructed this to cubic order, but it still remains to construct it to higher orders, to cubic order in the fields. And so the remaining point I want to discuss is, that we've already discussed, is how much of this is special to tori. The winding modes of the strings and the T-duality relating those winding modes to momentum modes seem very special, and hence in the resulting T-duality seem to be very special for tori. So other topologies may not have any winding modes at all, or may have different numbers of momenta and winding. And so the question about what if any of this goes over to this picture remains. And so then the duality symmetry, which as we've seen appears to give deep insight into the stringy geometry and how the strings work in very particular backgrounds, seems to be very different in very different backgrounds. I gave examples of T4 and K3. Other examples give other kinds of structures which again seem to be difficult to fit into the same general framework. But to summarize, I think what we've seen is that thinking about these symmetries has led to a lot of insights and a lot of understanding of rather novel and interesting and intrinsically stringy structure which might be arising. But it also tells us how much remains to be understood about string theory or M theory, in particular trying to understand how these particular features, which seem to be inherent, intrinsic to particular backgrounds, might have a more general meaning. So I'll finish there and let Abdus have the last words. So a typical, so from time immemorial, man has desired to comprehend the complexity of nature in terms of as few elementary concepts as possible. And perhaps if he was looking at the way string theory has been developing, he might take the view that perhaps we need fewer concepts and a better understanding of what's happening at the most elementary and fundamental level. So thank you for your attention. Sorry?
Holographic principles and the role of hologram in string theory?
Yeah, that's a very interesting question. So so there's a whole other important development in string theory and indeed in quantum gravity, which I haven't talked about in this talk at all, which is that the understanding that the quantum gravity or string theory, at least in anti-de Sitter space, is could be understood holographically. There's a duality between theories in four-dimensional anti-de Sitter space with a three-dimensional conformal field theory. And I think it would be very interesting to understand how that would fit together with this story. So I've been talking about some of the structures which arise in particular kinds of backgrounds. I mentioned tori and K3. And I was also mentioning that the whole story seems to be rather background dependent, and in different backgrounds, different stories and different symmetries and different dualities emerge. And anti-de Sitter space is another example, as another geometry where the structure seems to be very different, and it would be very interesting and important to understand how what we've learned about gravity and string theory in anti-de Sitter space ties in with what we've learned about gravity and string theory, say on tori or on K3. So it's a good question, and it will be very interesting to see how that develops.
Any other questions? No, thanks,
Thank you.